Hello everyone and welcome to this webinar. This webinar is about the use of Mada Civil for creating a pre-stressed precast beam bridge. The bridge is located on a highly seismic region of Greece and will apply Eurocode 2 and Eurocode 8. About myself, I'm Dimitris Mouroukis. I have an MSc in Bridge Engineering from University of Surrey in England. I have 22 years of experience in bridge and structural engineering. I have experience in design and modeling for local and international infrastructure projects, especially in structural and seismic design for bridges, metro stations, and complex structures. Also, I am providing MADAS technical support for engineering firms in Greece. Omicron Kappa is a Greek multidisciplinary engineering consultancy offering civil and structural, geotechnical, tunnel, mining, and environmental engineering services. We have offices in Greece, Romania, Albania, and India. We are going to start modeling the bridge from defining the properties for material and for sections. Then we are going to input the tendon properties. For the deck and the piers, we are going to create by the use of PSC Composite Bridge Wizard. Then we are going to define the time-dependent properties in order to find the creep and the shrinkage for the construction stages, also the compressive strength. Then we'll see how we apply reinforcement on the cross-section of the deck. Also loadings like moving loadings, construction stage loadings, and the response spectrum for the earthquake analysis. Then we'll see how we can check the results for the load combinations, reactions, moving tracer, vibration mode shape, tendon losses, and we'll see how we create the report. Also, we see how we create the PLC design. About the bridge now. The bridge is a prestressed composite eye girder. It has three spans of about 31 meters each, so it's about the total length of the bridge about 93 meters. The width is 12 meters. We have discontinuous beams. For piers, we have an arrangement of two columns each, which is 1.7 meters in diameter and 5.10 meters center to center. The bridge, as I have told you, is at the Peloponnesos area near Kalamata, which is quite the seismic, it's highly seismic region, and also it's the bridge is crossing a river. Now, some drawings. We have five beams of 2.65 meters center to center. Each beam has a height of 1.75 meters, and on the top we have a deck slab of 0.25 meters depth. The beams are sitting on elastomeric anchored bearings, and also we have two double piers with a diameter of 1.7 meters and a height of 6.7 meters for each pier. The pad head is from concrete and the depth is 1.7 meters. 1.7 meters. And we have 8 reinforced concrete piles of 1 meter diameter and 10 meters length. Here also we can see how the bridge deck is modeled. Now the cross sections must be provided first for the main precast beams and the composite top slab. All details are provided, as you can see, through masks that we use from Midas Civil. So all the dimensions, with the help of some sketch that we have, can be applied, and we can create the cross sections very fast and very easy. Also, on the right hand side, we can see the composite section now that it's from the top slab and the previous imported beam. Then the prestress type and the prestress material are provided in the program. We can have two types of prestressing. We have pre-tension systems and post-tension systems. Each one has its own characteristics. Here we are going to use post-tension system that we are going to do it on site. So we have a 12-strand cable that we are going to use, and we provide the ultimate strength, the yield strength of the tendon, tendon type, material, the total tendon area, duct diameter, and also we apply the material of the prestress. Before we continue, let's move on to the program and see what steps have been done since now. Here we have already opened Midas Civil. You have the trim menu here. We have applied for the materials. So we have the deck for the piers. After the definition of material, we move on for the section. And here we do the main beam properties, geometric properties. As you can see, Midas has a lot of predefined cross sections that we can change each time. We have boss sections, half boss sections, multi-box sections, and also sections that you can import from the section design. Also here we defined piers, the pier cross section, a solid round, pier cap, diaphragm beam, and so also the composite section, which is a part from the top slab and the main beam, which we defined previously. So here we do import, and here is the cross section that we defined previously. We press import and it's imported on the composite section. Also, in order to have correct the creep and shrinkage of the section in the construction stages, we define the different material that it's in the top slab and in the beam. Also here we will add the cross section of the piles. And also the pile head thickness, which will be from finite element. So here we'll go to thickness, add, okay. Also we assign the tendon properties. We provide the tendon area, ultimate strength, yield strength, etc. in order to assign the tendon properties. Let's move on to the presentation. So the first step is to set up the materials and the section properties. Now the second step is to use the wizard, the PSC Composite Bridge Wizard. In the wizard, we have the first mask is the layer tab, which provides spam information, girder types, bridge width, modeling type, and the substructure support type in order to import and make the bridge deck. Also, we can give the elastic links, which will do the simulation of the bearings, and depending on the bearing dimension and according to calculations or the bearing provider, we can find what is the stiffness of the bearing, and we applied it to the wizard. Also, we provide the material of the pier, the section for the pier cup, the number of piers, and the height, and the spacing between piers. Now, the next one is the section tab, which provides deck thickness, number of girders, the girder offsets, we assign the girder sections, diaphragms, and the type of layout. So we see that we provide the deck thickness according to the drawing, which is 0.25 meters, the girder's offset, the distance between each girder, type of diaphragm, on the edge supports, on the pier support, and the intermediate space between the supports. And then we go to the tendon layout, which provides us the tendon arrangement and geometry of each tendon, which have 12 strands. Here we provide the geometry of the strand. We have used 3 tendons, also by the help of a sketch that Midas Civil has, and in table format we can provide the geometry of the tendon at the beginning, at the middle of the section, also how many tendons we have, what is the jacking stress at the beginning, and in what stage the grouting will be applied. So by the help of the drawing that we have, let's say, completed at the first stage, we do the geometry of the pre-stress tendon. Next, in the load tab, we provide DEG, non-components and composite dead loads, design moving loads and traffic lanes, and also the vehicle selection according to the code that you are going to use. Here we are using Eurocode, so we define the lanes in a 12-meter deck. There are 3 lanes that we are going to use. So we give the geometry of the middle width of each lane in order to define where the vehicle will pass. Now the traffic load can be inputted manually, and the steps are how to define the moving load code that we're going to use. We define traffic lanes, we define the vehicle loads that we are going to use. Also, we do the moving load cases and we set up the moving load analysis option, and then we perform the analysis. For example, here we have used the LM1, which is the main vehicle in Eurocode. This load is in the library of Mazda Civil. We have a library for road bridges and highway bridges and pedestrian bridges. Here we can see the pedestrian foot load that we can use on the edges of the deck. Then here are some information about the combinations. Also, with the wizard, the construction stage are created that can be defined according to the duration and according to the steps that we're going to, let's say, build the bridge. So the steps are activated on the stage 1. On stage 2, we have the main girder and the diaphragm. Then the decks are poured on the main beams and the wet concrete load is activated. Then you have the composite creation of the deck, and we have the long-term effects that we have to consider, which is 10,000 days. Also, except from the wizard, we can do manually in construction analysis, where we first create for each element, we assign each element in groups, we make the time-dependent material properties, we link the time-dependent material properties according to its code that we're going to use. We do construction stages and time steps. We apply composite section for construction stage. We set up construction stage analysis option, and then we run the analysis. For construction stage analysis, input is the time-dependent material properties, which is creep, shrinkage, strength gained. Mazda Civil has a lot of codes that can be used for creep and shrinkage. Here we have used Euro codes for creep. Here we have shrinkage, and so also we can see how the time-dependent materials function for strength. And then we assign time-dependent materials with these values in each material that we have used. So at the end, after we finish all the wizard, then our model is created. So let's have a look on the model itself, how this has been performed. So after we finish assigning our materials and our sections and the tendon properties, we go to structure, and here we have the wizard. Now I will load the properties of my bridge. Bridge wizard starts with a basic geometry of the bridge. Firstly, the user will see the Layout tab when using the wizard. Here we can choose a modeling method for superstructure and also whether to include elements for the substructure or not. For this bridge, the general geometry is set up with the piers to simplify the process of building the rest of the substructure, such as piles, caps, and piles. The input parameters can be obtained from concept design drawings. The elastic steel stiffness defines the boundary condition between the piers and the superstructure. One tip for using the wizard function is to identify and input all the materials and section properties in MetaCivil before using the wizard function to set up the geometry loading and staging faster. Next to the Layout tab, we can see the Section tab. Here the user can allocate the materials and section properties of the deck, girder, and bracing along with the deck thickness. Furthermore, the user can input detailed superstructure shapes such as the number of girders and the position of girders. A useful tool is to copy current girder data for other girders tab, or the user can duplicate the position data from one girder to all the other girders. This saves the user time from manually inputting the data. Here also you can see the tendon layout and the load tab. Over here the user can input typical design forces which will save the user time afterwards. This option allows the user to add loads such as self-weight, the weight of wet concrete, and the barrier. These dead loads can be applied to each construction phase automatically if the construction stage analysis is considered. Because the model is a highway bridge, moving loads such as traffic loads were also considered here. This can save the user time assigning them later on the process. And also here, as I have told you, these are the construction stages that are automatically done in MetaCivil. So after I completed all these steps, I press OK, and the model is created. As you can see here, we have a grillage model here with a piers, supports, links between the piers and the deck. Here we can see the supports, the elastic link between the two nodes. And here you can see the rigid link. Which is the beam height. Also, construction stages have been applied. You can check this is stage 1, stage 2. You can see that there is a slab activated. Now the deck slab is activated. And this is the final stage. Also, you can see here groups that have been done. Tendons. You can check the tendon. Here, first span, second span, third span. So let's move on back to the presentation. After the glass model is created, then we have the creation of grillage model. So the structure is analyzed as a number of longitudinal and transverse beams elements on a single or more spans with rigidly interconnected nodes. So the grid is in longitudinal and transverse beams. Longitudinal beams are centers of little less than lane width. If we have a deck, then we have a continuous beam. Here we see how we create with the complete model. The bridge is simulated using elastic links in the bearing position and rigid links for the beam height. The next step is the input of desired reinforcement for finding section capacity. We can see that the part 1 is the main beam and part 2 is the top slab. Here is the mask that we provide the reinforcement at the slab and on the beam section, the longitudinal reinforcement. Also, we apply and for the shear force reinforcement in order to find the shear force capacity of the beam. Here we have to change the load type of loadings in order to make, instead of construction stage load, we provide each load a specific type. In order when do the combination, the Mada Civil can provide the correct combinations and safety factors. Lots of vehicles, according to several codes, can be applied, and the vehicles automatically placed to maximum or minimum forces on the elements. Here, according to what lanes we have defined, the loads are moving on these lanes, LM1, and the footway and the remaining area is applied for the remaining load. Now let's proceed for the dynamic analysis. We have to convert self-weight to masses. Also, additional loads can be converted automatically to masses in order to take into account of the dynamic analysis. Here we convert x and y of the self-weight of the structure in order to participate in the lateral movement during earthquake. Design of response spectrum with a spectrum of Eurocode is assigned. As you can see, all the characteristics of the response spectrum are applied in Mada Civil. Also, load combinations are created automatically. When we assign each load case, we choose the correct characteristic, so combinations are created automatically. Some adjustments may be required afterwards. So here we define permanent loads, pre-stress load settlements, and variable loads, and according to each category, Mada Civil can create the combination. After running the analysis, you can check the results on the beams, on the decks, on the supports. Also, in a table format, you can see the concurrent forces for, let's say, maximum bending moment of the vehicle and every other result that we need. Also, for the vibration mode shape of the dynamic analysis, we need to achieve a maximum of 90% mass participation in all directions. So we check the sum in X and Y in the vibration mode shape table. And we adjust the eigen analysis control if either one of the directions did not reach 90%. So let's now proceed to our model. After the creation of the deck and the pier, we need also to create the soil structure interaction. In order to achieve this, we have to model the foundation and the pile head and the pile itself. One easy way to do this is through DXF files. So let's see how we can do this. We export our model in AutoCAD DXF file. And then by using an AutoCAD file, we load the DXF. Here we have our bridge in a DXF file. Here we are going to create a rectangular shape for the pile head. And then we create the piles. 10 meters length, and then we'll offset. So the foundation has been created. Now let's import this in Mada Civil. We choose our file. First, we choose to import the piles. Now, because we haven't assigned any cross-section, we will define a new cross-section for the pile. Okay. Now the pile has imported. Wrong section. Okay, now it's correct. and then the peer cup. We have to find thickness of the peer cup, the pile cup. Okay. So for the first pier, we have assigned the foundation. Now this foundation must be assigned to a group in order to activate on the correct construction stage, which is this one. Assign plus. So every beam element and every node has been assigned on this group. We'll divide this element in order to provide the supports now. Okay. And now the boundaries. We'll change the units. Let's add 10,000. In XY direction. We'll assign this in this boundary support group here in order to be activated in construction stage. And then in here and in Z direction. Okay. Also now, because from the bridge wizard we have supports here, these supports must be deleted now. Okay. And we are going to create meshing for the pier cup. Meshing has been created. You can see that common nodes have been created. There is no duplicate elements. Let's activate this of the correct construction stage, and we'll copy this to the second supports. You copy from here to here, which is 33 meters. We copy node attributes, apply. Oops. And now the supports have also been created. Also, we are going to activate this to assign this on the correct stage. So let's have a look if everything is correct now. Yes, everything is been activated correctly. Let's check also and the boundaries. Okay, stage 1 and stage 2. Excellent. So now we'll proceed with running the analysis. Before running the analysis, let me show you how you defined the section reinforcement. We go to the section manager, and here we can see the composite beam. We have the composite beam for the central section of the beam, and you have the composite beam for the left and right hand side. So an easy way to use reinforcement is by using guideline lines when we define, let's say, 40 centimeters of cover on the reinforcement, and we have the creation of this guideline which will help us distribute the reinforcement. So here, let's say that I have every 150 millimeters a bar of, let's say, 360, and this is part 1 and the top slab is part 2. So I will choose part 1 and I use also edge bars. Okay. Then okay, and then I will choose part 2. Let's say 12. No. Okay. This is how we define reinforcement on the cross section. Now let's run the analysis. After running the analysis, let's have a look on summary results. Here we can check some results during the construction stages. Let's see some building moment diagrams. Okay, shear weight has been applied. You can also see some creep, some shrinkage. Okay, stage 4. Dead load has been increased. Let's make it 0.1. Okay, now that we have concluded and that our analysis is correct, I'll check and some building moment diagrams for earthquake. Okay. Okay. Also for the earthquake analysis, let's have a look on the deformations. This is the earthquake XX direction. Let's have a look at the Y direction also. Okay. Now we shall proceed on the deck checks for the Eurocode. Then we'll go back to our presentation. Here we have the design checks for the PSE beam according to Eurocode. We have checks for all output parameters in ultimate limit state and serviceability limit state. In table format, we can view the section bending strength, For the worst load case scenario, positive and negative bending moments are taken in account, and the moment resistance is calculated according to the also reinforcement used. Also, and the shear strength of the beam is checked. For the stress verification at the construction stage should be satisfied. The most critical compressor strength during construction should be less than the allowable compressive stress before losses of the pre-stressing. Here we can see that the compressive strength of concrete for the post-tension is K1 FCK tough, where for K1 has a value of 0.6, and FCK is the concrete compressive strength at time t. As you can see, all the checks are satisfied. Also, here we have the tensile strengths at the serviceability limit state. We have the verification of the induced stresses and the allowable stresses of tendon by tendon group. Here we have before losses, tendon stress at the anchor right after grouting should be less than the allowable stress. Also, after immediate losses, the maximum tendon stresses should be less than the allowable stresses. And after all losses, maximum tendon stress be less than allowable stresses. Here we can see that the stresses are satisfied, and also at the serviceability limit state we have the crack width check, which should be less than 0.0 millimeters. Using the diagram for PSE beams checks, we can check the stresses at the top and the bottom fiber of the cross sections of our beam. Also, we have the allowable stresses and we have the applied stresses in order to check if they are less than the allowable values. Also, we have the creation of an analytical report which all the checks are provided on a spreadsheet file. So the design conditions, the ultimate limit state resistant, the shear resistant, the torsion and the crack width is provided to us on a very elegant form, and we can use it in order to produce the report. So let's check in our model, go to our PSE. Here we have the parameters that we have checked. We have applied our materials for our cross sections. Here we define which members we want to check for our structure, for our deck. I have chosen this beam. We can check it on a tabular form also, which member have been selected. And also here I have in which beams I want the output to be as a format of my report. Short long-term load cases have been automatically applied, and the serviceability load combination type are also on the quasi-permanent, frequent, and characteristic form. So as I perform the design, it will take some time to prepare us the output. Also, we shall now check the reinforcement for the piers. We have choose Eurocode 2. We choose the design code, and also that we consider axial moment interaction for plate columns. Cooking materials. The maximum recommended by the code rebar ratio. We have the pier. We choose a cover of 40 centimeters, and for the shear, 4 numbers of V16, and for the piles, 50 centimeters with a V12 spiral. Now we will perform the design. Here are our check. I'll make this centimeter. We need 95 centimeters for the section, and also we can see the detailed report with all load cases and all the calculations on an elegant form. So that was my presentation for today. I would like to thank you all for being with us, and I hope to see you soon. Thank you very much.